Hello everyone, welcome to today's Maths Club talk by Nikhil. He's a third year student here at SMUSI Bangalore, and his interests are in algebra and combinatorics. And this is going to be the second talk of the Introduction to Combinatorial Game Theory lecture series. And this lecture is going to be on the Sprague-Grundy Theorem. Over to Nikhil.
Thank you, Devansh. So this is the second talk on combinatorial game theory, and so today, as I said in the last talk, we are going to look at several things, including the definitions of game itself. Because last time what happened is we saw combinatorial games, what they are informally, they have two-player games with perfect information and no randomness, and we saw several examples, and most importantly, we saw this example of the name game, and we proved Bowden's theorem, which allowed us to get winning strategy in the game of names. But again, towards the end of the last talk, as I mentioned, that all of this, one can formalize it even more, one can define games more strictly, and I mentioned towards the end the Sprague-Grundy Theorem, which in some sense talks about impartial games being equivalent to names. Today we are going to look at, formalize all of this and then write down the proper statement of Sprague-Grundy Theorem and prove it. Okay, so to start, I want to say this. I have to say a few things here. So the first thing is, so from now on, so when we are studying combinatorial games, we want to study combinatorial games, and there are several different games that we know, like named Kyle, Stomp, and so one could in fact be like, okay, let me study all of these differently, and study all of them like we studied name, we study Kyle, study Stomp, but that has several demerits. But what we are going to do is instead look at some sort of universal theory where we could study all these games coming from different rules and stuff like that, all at once using the language that we'll develop today. Okay. So the first thing I want to emphasize is that from now on we wouldn't call games, but we'll call positions in games. And so, for example, let's say I have a name position, and let's say I have a chomp position. Let's say I have a name position and a chomp position. Well, again, I will call both of these just games, and then a move like removing 2 points here or cutting some squares here is really just, we'll regard them as rules that dictate how to go from one game to another game. And so so this is a game, and then if I move this is another game, and okay. And the other thing that I want to mention is that, as I said last time, we want to assign values to games. So I gave that example of the grid game, where we assign values like +1, -1, and 0, and so on, where it was like, okay, well, if it is positive, then A wins no matter who starts. If it was negative, then B wins no matter who starts. And if it's 0, then second player wins. And stuff like this. Now, so to each game, which now we mean a game position. So to each game which I'll again game position more specifically, we'll assign a value to it, and then we'll study how these values add, how these values compare, and so on. And the distinction that I want to note now is that I will regard a game and its game value as equal. So whatever the value of this is, I'll just say this is equal to this. And why is that? And that is because the way we are going to study things, there is really no there's really no point in distinguishing a game from its game value, because if you want to see how this game interacts with other things, then well, we just need to see how the value behaves with other games. Okay, and another advantage of this approach is that if I have two positions that are in some sense really the same, which in somewhat more fancy jargon isomorphic. For example, let's say I have a nim position of 3 coins, and let's say I have a chomp position. Then these two positions are really isomorphic, in that a move here is to, there's 3 things on either side, and a move is to make it 2, 1 or 0. So these two games are really the same, and we want to regard them as the same, and that justifies, when I give this a value and when I give this a value, I'll give them the same value. So I'll, sort of this equalities like this make sense. But the twist is, I'll also sometimes, for some reasons, which we will see soon and understand soon, I'll also regard some non-isomorphic games as equals. And why? And that will come soon. So, but we'll get to it slowly. But for now, I want to continue, and then I want to describe the central notation of the subject. So let's say, okay. So suppose I have a game G. What do I want? I want to describe it, and the way I am going to describe it is I'm going to write for a game G. I'm going to write this expression, and what this means is and so there are 2 players in all of our combinatorial games. So let's call those players they're conventionally called left and right. So okay. So again, I want to eliminate I don't want to bother about looking at different rule sets. Like this game moves to other games by some sort of rule set given by the nim rules, and this goes to other games by chomp rules. But I don't want to bother about these, and so what I'll do is I'll just describe a game by things that the players can go to. So I'll write for a game G these two separated sets. On one side I have the games that left can go to, which means when left plays a move, what are all the things that left can go to, and over here I have games that right can go to. And we'll see more examples of this notation soon. But before examples, I want to introduce one more notion, which is the notion of sum. The notion of sum is very central to the subject, and that is what the entire theory will revolve around. But okay, so given a game G, given a game H, for the last time I'm saying this, but a game G is a position in a certain rules or whatever, in a certain rule set, and H is again a position in not necessarily the same but some other rule set. And how does this game work? The game works as follows. A move for a player is to move in either of the components, either of G or H, and and then again the normal play will be followed, which means whoever cannot make a move loses. So for example, if I have, let's say I have an nim position of 2 and 4 coins like this, and then I have a chomp position like this. Then in the sum, what happens is, if I'm a player, a move for me is to pick one of these components and make a valid move in either of them. So for example, let's say if I pick this component, pick this square, I'll remove this, and then the next player on their turn can pick this component instead and then remove, say, these 2 points. And the game will go on like this, and when one cannot make a move, which means one cannot make a move in either of them, then they lose. Okay, so this is about the sum, and I want to emphasize that the sum is, well, one could have considered other choices, which one, for example, what if a player had to move in both of them, and so on. But yeah, and that is, they also lead to several interesting theories on their own, but somehow this turned out to be the one we use, and this is very standard. This is called more properly destructive sum, but we just refer to it as sum because we are not going to see any other sums. Okay. So, and one more thing I would like to say here is that not just 2 games, I could add any number of games and it behaves like that same way. A move is to pick one of these GIs and make a move there. Okay. So now let's go to examples and understand this notation better. So for example, let's look at, so for these examples, let me introduce another commutative game. So let's see. So the game is now Domineering, and the way it works is you have a grid. You have a grid, and then again you have your players left and right. Left has vertical pieces, vertical 2 by 1 pieces. Right has horizontal pieces, 2 by 1 dominoes or whatever. So a move for either player is to put one of their, okay, and let me use color. So a move for a player is to put any of their, so left has several of these pieces, right has several of these pieces. A move is to put one of their pieces here. So for example, if left starts, let's play a piece here, and then right could play a piece here. And again, overlapping is of course not allowed, so this is not a move for left right anymore. So let's say left plays here, and then right plays here, and let's say left plays here, and so on. Of course, the game will keep going. Okay, so so these are the rules, and let's again, as usual, we are going to work on the normal thing, whoever cannot make a move loses. So let's see some positions. So let's consider a 1 by 1 grid. What could be simpler than this? So if you have a 1 by 1 grid, well, I want to write on this side things that left can go to, and on that side things that right can go to. But well, clearly left or right, no one can make any moves here. So there should be nothing here, and in fact this is the notation. So when there's an empty, so yeah, a game is really just a pair of 2 sets, and this is just the pair empty set from empty set. Okay, so and we'll call this 0. Why 0? And the reason behind this is, well, I mean, it will become more clear later on, but one could see it because if you have, say, a game like, if you have, say, any game G, and you consider the sum G plus 0, well, you notice that since no player can, neither player can make any move on 0, it's really just the same as playing G. So this in some sense is just G. In fact, whenever we define equality, this will turn out to be equal to G. But it's very intuitively clear that we'll demand this in this speed. So in that sense, we'll call it 0. And then the next thing is, let's say, a 2 by 1. Well, here, right still does not have any moves, but left has a move, and that move is to put a piece here. I don't think that here. Okay, so for this game, I have this, and okay, so right doesn't have any option, so I'll just leave it empty here, and here left is one option, and that is to go to this, but notice that this is just 0, this is really just 0, because neither player can make a move from here, so I'll call this, and this I'll also give a familiar name, and I'll call it 1. And again, so let me motivate why I am calling it 1. So let's say if I have some name g and I consider g plus 1, how does playing on this look like? Well, right cannot make a move on 1 ever, but left can. And so essentially left and right continue to play g unless left at some point decides to play in 1. And whenever left decides to play in 1, left goes to 0, and so that just vanishes. So this 1 is like one free move for left that left can use at any point of playing g. It's like they are playing g, but with left having a move pass at any point. Okay. So in that way, I'll call it 1 because it's like left has a one move advantage over right, or well, left gains a one move advantage if this is added to something, which makes sense. And in a similar spirit, this game, which now left doesn't have any options but right does, and that is to fill this up. And this is again 0 by the same thing. And this I'll like to call -1 for the exact same thing. Again, the plus and minus now are just sort of conventions that plus is for left and minus is for right. But essentially 1 is a free move for left, and -1 is one free move for right. So now let's look at. So now I want to say this. If I'm calling this 1, if I have a 1, if I have a -1, and if I have a 0, I want this equation to make sense. I want this equation to make sense, but the problem is, well, these two games are really not the same, because in this players can make a move. Left has one move, right has one move, but in this neither of the players have any moves. So these two games are not isomorphic; they are not the same. And again, this is more motivation for why we need to, define equality more properly. So we want to define these two games as being equal, such that this familiar identity becomes true. Okay. So continuing on, let's go to a 2 by 2 bit, and then here, one might say there are two moves for left, but they are the same up to symmetry. So I'll just write 1, and now I'll write it this way. I should write this grid with this field by blue, but no moves can be made in that component, so I'll just regard it as this. This after left makes a move is just the same as this, and similarly right after right makes a move is this. So this is 1, this is -1. So this is 1 bar -1. Okay. Now again, you might be expecting me to give this a label of a familiar number like I did for 0, 1 and -1, but I would not. And that is not because of some arbitrary choice, but it's rather that, well, I cannot really give it a familiar, a familiar integer, because it doesn't behave when adding and comparing. It doesn't behave like an integer, or like a rational number or something like that. So no familiar value that we know, no real number, for example, it makes sense to assign it. So we'll just keep it like this, and this again, it's not it's not ill-defined or something. This is a very strong and this is a very precise definition of this game. Okay. And now at this point, and in fact, okay, I'll mention this. So in the subject of combinatorial game theory, I'm not going to do this, but one can do this, and one can define what it means for a game to be a number, and under that definition, this is not a number. Numbers include essentially these familiar values like this. Okay. So before going to the next, just increasing the grade size to 3/2, I want to emphasize that, so if you have a domineering game that goes on like this, let me draw this. So if you have a domineering game that is going on, then you notice that after some point, it breaks down into several disjoint components. For example, this really has broken down into this on the top plus this on the side and plus this here. So this, and this here. And so this and this are really, this and this sum of three games is really the same, because again a move in this game can only affect one of these components. It's only to move in one of these components, and that's exactly what the disjunctive sum means. And this was one of the this is one of the founding ideas of the subject. A game often breaks down into disjoint components where moves can only affect one of the components, and so it makes sense to study disjunctive sum, and this is why I studied revolves around disjunctive sums. Okay. And this also tells us that it's worthwhile looking at non-rectangular positions, because if I want to study this, I'll have to study this, and this, and so not just rectangular grids, but I should rather in fact study grids like this. So let's see. Let me erase this. So let's say I have a rectangular grid, not non-rectangular grid like this. Then again, left has only one move, that is to go here, and that leaves 0. And right again has similarly only one move, and that is to 0 as well. So this is 0 bar 0. I'll give this a familiar name, though. I'll give this a name, but not a familiar one. I'll not give it an integer name because it doesn't behave like an integer, but I'll give this a name. I'll give this name star. I'll give this the name star. So star is the game where both left and right, they have only one move, and that is to go to 0. Okay. Now okay, and so let's do one more example, a little more complicated. So let's say I have a 3/2 grid. Now, what happens? So left has 4 moves, you can see, and again I like to emphasize that all those moves are the same up to symmetry, because moving this leaves a grid like this, but if instead left had moved here, this grid, though looks different, is really the same. So I will make no distinction. You can, if you don't see it immediately, you can try to include both things, and you'll notice that it doesn't make a difference. So yeah, so let's see. So on this side I have this, And on the other side, now right has really two distinct moves. One is to go in the top or the bottom, and that leaves the 2 to get right here. And the other move is to go to the middle one, breaking it down into 2 pieces. And these 2 pieces on their own are -1s and -1. And so, well, and the game that remains is their sum. So I'll just call it -2. So I have the 2 by 2 grid, which is this. And I have -2. Okay. And now again, so I mentioned this in the last talk towards the end, that the scheme of assigning values is very universal and it's very recursive. And this is exactly, and you see this in action right now. You see, I'm trying to give this a value, and in that I'm like, okay, I face this other position while assigning this value, and now I'll do the same thing to this. So if I look at this, what do I have here? Here, left has 2 moves. One is to go here, that leaves -1. The other is to go here, which leaves 0. These 2 squares are disjoint. There's no moves there. No more moves after this. Right has only 1 move, that is to go here, and so that leaves +1. And so this game is so this game is really this. Okay. And this seems somewhat complicated, but and that is true, but there are ways to simplify this, and those are exactly the ways that we'll see not today but in the next talk. The next talk is all about simplifying some complicated things that look like this. Okay, so yeah, this is okay. The next thing I want to do is I want to look at just this one for some time, and that will motivate certain things. So I think this notation we understand, at least we somewhat understand it pretty well now. So I want to look at -1, 0, bar 1. Okay, I want to see this. Okay. So what am I going to do here? I'm going to assure you that okay, this is a familiar value, but what is it? Let's work it ourselves slowly. So the first thing we want to see is G positive, is G negative, and so on. So is G positive? Well, if it is positive, then we'll sort of want, based on all these things, that since 1 means advantage for left, positive things really mean advantage for left, plus and minus. So does left win advantage here? Does left win no matter who starts? And that is true, because if left starts, then left just goes to 0 and wins. And because from 0, right cannot make a move. And if right starts, right has to go to 1, and left wins from 1. So G is positive. Well, the next question is G1 then? Because if it's a positive, well, we are not seeing so many examples. We only know, okay, well, 1 seems positive. It might be 1. So is G1? Well, so for the next, for the purpose of this example, I'm going to be a little bit imprecise, but I'll rather just do a lot of hand-wavy manipulations, which can all be justified later on when we give the proper definitions, but this is all motivation. So if G was -1, then we'll expect this to be 0. And I think I erased it already, but from the last talk we have some sort of understanding that 0 games are the games where the second player wins. So the player goes second wins. So let's have a look what happens here. So if left starts, left cannot make a move in -1, left can only make a move in G. in G left can move to -1 or 0, and going to 0 leaves -1 and going to -1 leaves -2. And yeah, both of these are really bad right principles. What I mentioned, right makes move though. So right can go to here or go to here, but if so, let's say right moves in G. If right moves in G, the move in G has to be to 1, leaving overall 1 plus -1, which again the hand waviness is here, so I'll call this 0. And since it's 0, right wins because left cannot make a move. Or you could just analyze this again, because from here, if left has to move, left can only make a move here, leaving 0 here, and then right will have -1, and so right wins. So what we notice is that right wins in either way. So well then it will make sense to say at G plus -1 is less than 0, and by the hand waving, by some hand waving, we know, well, this allows us to conclude G is smaller than 1. So far we have that G is something which is bigger than 0, it's positive, but it's smaller than 1. And okay, what can we do? Now we want to give it again. I remind you, I said that this has a familiar value, and it's a value between 0 and 1. Well, let's just make a guess. Let's make a guess that G is half. And there is some problem with this. Well, kind of. So like, as I said, 1 sort of denotes 1 free move, -1 sorts of denote well, 1 free move for right. Well, if I told you to interpret things this way, how do I interpret half? There can't be half a move, right? And well, one way to see this is that the point is exactly this. Half move is half as worth as a full move for left. So in that, if I add half to itself, that really becomes like 1. So okay, back to this. If I want to check this from the very little tools that we have, the only way to see this is if this becomes 0, then we can convince ourselves that G is half. And again, let's just work with the vague intuition that 0 means the second level. So let's analyze this. Left move is in, well, left can make a move in -1. It has to be in either of the G's, and then I really have to consider only one possibility because yeah, it's symmetric. So in left, in G, can make a move to -1 or 0. I'm not going to, so well, it is intuitively clear that 0 is better for left than -1. We'll make this more precise later on, but intuitively, well, why would you want to give your opponent a free move when you cannot? So I'm not going to do the analysis with the -1. That you can do it yourself if you want, but for now, let's just say left goes to 0, and so the game that remains is 0 plus G plus -1, and G plus -1, as we saw, is negative. Right wins always, so right wins. What happens when right makes a move? Right has 2 moves here, so I have to consider 2 possibilities. One possibility is to make a move in -1, which leaves G plus G. -1 after a move becomes 0. So G plus G is positive, so left wins. Since G is positive, well, again, intuitively we expect G plus G to be positive as well. Left wins. And the other move that right has is to move in G. In G, right can only move to 1. So that leaves 1 plus G plus -1. So well, yeah, again, and 1 plus minus 1 you kind of expect it to be 0, and all that remains is g, and g is again positive, so let's finish. So let's finish. So whoever it's a second element, left starts, left loses, right starts, right loses. So in that way we'll truly want it to be 0, and so by basic algebra we'll want this to be g to be half. So as you see, these games, if they have a value that we know, it doesn't have to be an integer, it can be something like half. And I'll leave it to you to come up with examples where it makes sense to assign it 1/4 or 1/8 or 3/4 or something like that. Okay, so the next thing is, well, the definitions. So let me, okay. So the next, so I want to move to the definitions now. With all of these examples, I think we are enough familiar with this notation and how to work with it. So now let's see examples. No, not examples, I mean definitions. So I want to define games. I want to define combinatorial games. And okay, and the point is all of these games, they live in an abstract mathematical space where games are some abstract objects, which so we wouldn't regard, well, whatever we are going to define, this will be a game, and this by our analysis is equal to this. So yeah, and to define, so the definition, oh, I have erased it. So the definition is as follows: G the definition is G is a game if G looks like this, where these are games as well. Well, this certainly makes sense. I mean, this is what you expect, but the definition doesn't make sense because I'm using games to define games, right? And you would be right, but the point is this definition is fine because it's an inductive definition. How exactly is it inductive? That we'll see in a moment. But you could imagine it's like, okay, well, let's have this analogy. Suppose you are the god of the universe where you want to define games, and I told you that this is a rule you need to follow, and then you are like okay, you have the task to create games, and the way to create a game is to put several of the games you already have and put them in these boxes and create new games, but you don't have any games to start. So what do you do? And what you do is, well, you do this. This is a game. Why? Because everything here is a game. Everything here, there's nothing here, so there's nothing to check. So this is a game by this definition itself. And this is the base case, formally speaking. So this is and this as we saw already, we'll call this 0. Okay, I'm going to need some space. Okay. Let me just erase this, I think. extra game by the scheme. What else is? Well, now I have a game 0. So now I can give more games. I can now create 3 more games. And let's give these some sort of, let's give them some sort of hierarchy. So day 0 is when you had nothing and so you created 0. Day 1 is when you have 0 and nothing, so you could create these 3 games. This game, as we have already seen, is number 1, this is -1, and this is 1. And then on day 2, now you have a lot of choices. You have 4 games so far, 0, 1, -1 and star. And to use that scheme you have to put games on this side and games on this side. On this side you have thus 16, 2 to the 4, 16 choices. On this side you have 16 more choices. So overall you have 256 choices. And well, we have 4 of them already here. So you expect 252 new games. I have put a question mark here because, well, it turns out, well, as I said, I'm going to define equality of games, and under the definition of equality, turns out that there's only 18 new games. So it turns out there's only 18 new games after I've defined equality. So many of these turn out to be equal to some other of these, and so you only remain with 18 new games. And some of these, for example, are 2, which is 1 bar nothing, and 2 intuitively is 2 free moves for left, and this is exactly what it is, right? Because right should not be able to make a move from here, and left, whenever left makes a move, one should be what is remaining. And similarly, we have this. We also have our familiar half. We have half. You could also have -half, but I'm not going to write that. I think let's leave it as an exercise for you to come up with. You could very easily do it after the end of this lecture. So yeah. Okay. And then on day 3 you have even more choices. Several choices now, 18 plus 4, 22, and then you have 2 to the 44. That is a lot amount of choices. And in fact, after even defining the equality, there's also like 1,000 and around 1,800 new games created. Okay, so this is the recursive construction, and it will keep on going like this. Yeah, and with this, I'll give a definition. So I can write this somewhat more formally. I could write this formally, and that will be defining okay, one could write down this process formally, but I'm not going to write it in the most precise way. But G is on, I'll use this. G is a game born on day n, where these are games born before day. And on day 0 again there is nothing, so and this is again on day 0, this is our basic. And so again, pretty much everything we do is going to be an inductive proof. Pretty much every theorem that we are going to see, it's going to have an inductive proof that will induct with the levels of proving it at each day. So for that reason, I'll need this little definition here. If I have a game G, I will denote the birthday of G called BG equal n if G is born on day n. So this is what we will use to properly write our induction proofs, and then we are not going to look at all games, we are only going to look at a certain class of games, and those are called short games. I'll say that a game G is short if it was born on a non-negative integer day. And this definition might seem a little strange in the first sight, because what else is there? Well, of course, there's only the non-negative days, right? And well, that would be wrong because there are more days. People who are familiar with these things called von Neumann ordinals will know that if I treat 0, 1 and 2 as ordinals, after all the non-negative days, I'll have the omega, and then I'll have the omega plus 1, omega plus 2, and so on. And so the definition of short restricts to exactly whatever is happening before this. And well, if you don't know what ordinals are, it's perfectly fine because we are not going to deal with this at all. We are only going to restrict our attention to games that were born before, on things that we are familiar with, and those are short games. So from now on, all games are short. And okay, let me just give one example of something that is born here. That is 1 by 3. So what is it exactly? It is one by 3 is defined as this game. And again, it is really 1 by 3 in the sense that if I add it to itself 3 times, it gives me 1. And well, you notice there's a dot here and here. So there's infinitely many options on either side. And this certainly cannot be short because well, if it is born on day n, there's only finitely many games born before day n. So this is certainly not short. But this is a game, it makes sense. The options from 1 by 3 are to go to any of these. If you want, I can give you a more familiar example as well. You could also have this game. It's very simple. Where a move for left is to go to any non-negative integer. Left could go to any non-negative integer, while right doesn't have anything. This is also a game. And these games are not short, but they are also interesting in their own right. We are not going to look at them. Some definitions that we are going to see work fine for things born after day n, but some of them don't. But yeah, so we are only going to look at short games. And the good thing about short games is they are bound to end. A short game, if left and right are playing, it can never keep going on because there's only at each step there's only finitely many things, and of course when you move from a game born on day n, you go to a game born before day n, and so on. So the days are decreasing. So at some point the game will hit an end where either left is 1 or right is 1. Okay. The next thing I want to talk about is how to add games formally. So now that we have a working definition of games, and okay, let me say this. So now I want to define the sum. So let's say I have a game G. I denote G like this: fancy G L, fancy G superscript R. Fancy G superscript L is just, which I just referred to GL. So this just means the set of all the A, B, C, and whatever, and the fancy G R is just X, Y, Z, and so on. So these are sets. These are two sets of games born before G was. And let's say I have another game H. Fancy HL, fancy HR. Then I want to define G plus H. G plus H intuitively is the set of all, so if a move from, what is a move from G plus H for left? A move is to go to any of the things here plus keeping H intact, or any of the things here plus G. So it's really so this is my definition. Before I go into the problematic part about having sums to define sums, I'll mention and I'll mention this. So this GL is a set, H is a game, so this doesn't make sense as it is. But what this really is I take every GL in fancy GL and I take any left option of G, I add it to H. So this set just means adding H to each element of the set. Similarly, this and this are defined. And once I have this definition, this definition at least makes sense, because a move from G plus H to go to something like this or something like G plus HL. And similarly on this side. Now to get to the part about, I've used sums to define sums, and so, well, again, as I said earlier, since the definition of game is inductive, everything is going to be inductive, even the definition. So this definition is inductive, and one could do this definition by inducting on this quantity. Because if I'm looking at this quantity, for this sum is B of GL plus B of H. B of GL is certainly smaller than B of G. So the corresponding quantity for this is smaller than the corresponding quantity of this, and same for all of these. So by induction, I can assume that all of these things are defined, and then I can define this. In the base case, I'll never mention a base case in any of the proofs, because the base case is when the involved sets are empty. And when the involved sets are empty, there is nothing to do. You can try to convince yourself by looking at some examples. So anyway, let me go on to examples. Let me mention the base case here somewhat explicitly. So the base case here is when this is 0. When this is 0, both G and H, both B and BG and BH are 0, which means both G and H are 0. And 0 plus 0, we all can see what that is, right? So I will by exactly this definition, and so the corresponding GL for 0 is empty, and all of these sets are empty. And since the sets are defined this way, if this is empty, then this is also empty. So everything here is empty. And okay, by the way, this is comma is just union. This union to set. Okay, so this is the base case, and there is nothing too deep here. 0 plus 0 is 0. Okay, but and one more thing to note is that this is clearly commutative. G plus H is very clearly H plus G. It's also associative, but that I leave for you to check. But for now, I'll move on and do a little result. Okay, so this we don't need anymore. theorem. Let's do a proper proof. Let's do our first theorem. G plus 0 is G. So this is exactly why we called 0, 0. And the proof of this is G plus 0. What is it by definition? By definition, it's this, which in our case will just be comma this, but you notice that HL for 0 is empty. So this set is really empty and I am not doing anything here. So let me write down one more step and then we all know it's not really here. So let me write it down this way, it's G plus 0L, but there's nothing here, so I'll just cut it out. Similarly, so all I have here's the min part. Well, I'll assume I'll prove this. I'll use induction on B of G. Then I want to show this. So assume this is true for all G with B of G is smaller than n. And the base case again I mentioned, we don't need to mention, it's already done. So assume it's true for all B of G is smaller than n. And notice that things here and things here, the birthdays are strictly smaller than n. And so the theorem holds for them. And so this really is just this. And this is just C. Okay. So this proves this theorem, and this is exactly what we expect 0 to behave like. Okay. Okay, let's do one more theorem. And okay, fine. So let's do it here. Theorem 1 plus 1 is equal to 2, but this time it means something which is very different. 1 is that game right there, 2 is this game right here, and the sum is defined like this. And we need to establish 1 plus 1 equals to 2. 1 plus 1 by definition is 1L plus 1 bar 1R plus 1. Sure. One plus one is equal to this. I should have ideally mentioned 1 plus 1L and separately, but by commutativity it doesn't really matter. So yeah, okay. 1L is just one. This 1L, the set is just a singleton set with 0 to its infinity. So what we have here is just 0 plus 1. 1R on the other hand is empty. So this set is empty. 0 plus 1 by this theorem is 1. And 1 bar nothing is 2. And this proves the theorem. Thus, 1 plus 1 equals 2 as games. Okay. And then the next question is very natural. If you have done some bit of, well, algebra or even analysis, any kind of math, when you notice that it's a very common theme. If you have a set and on that set you have a binary operation, and you have an element and you have identity, so let's say you have a set of all games, you have this operation plus, you have an additive identity. You add 0 to any game, it remains the game itself. And yeah, so and it's commutative and associative as well, which I mentioned over here. But so then the question, very natural question is, can I complete this and give it a group structure? Can I have that the set of all games is an abelian group under this operation plus? If you don't know what that means, it's fine. All that really means is that for every game G, can I find the H such that G plus H is 0? And the answer is yes. Though again, so the point is all of the other things, commutativity, associativity, and additivity, they all can be proven directly from the definition. But the existence of additive inverse cannot be. You need to, and that is exactly where we need to redefine equality. So as you see again and again, redefining equality has a lot of merit to it. So if I have a game G, I define minus G to be I define it to be minus GR bar minus GL. Again, a very recursive definition. Minus GR just means minus of everything in the set, and same thing here. And since the birthplace of things here are strictly smaller than the birthplace of G, the definition is fine. It's inductive again. And minus of 0 is 0, that's the base case. So why is G plus minus G 0? Well, certainly not exactly 0, but one can notice, which I'll do in a moment, that under the redefined notion of equality, it is indeed true. So, okay, we'll see it in a moment. So let's go on to the next thing for now, which is comparison. Do I want to keep this? No, I don't want to. Yeah. Okay, I want to define the next thing, comparison. So let G be a game. I say G is positive if let me just write these down and then I'll explain what they mean in a moment. Okay, so comparison is positive games are those where left can win no matter who starts, negative games are those where right can win no matter who starts, zero games are those where the player to move second wins regardless of left and right, and G is confused with zero if the player to move first wins. If this happens we call it positive. If this happens, we call it negative. This we call 0, and this we call fuzzy. Okay. So we have these four. So as I said I mentioned in the last class, we give a partial order to the set of all games, and this is how the partial order works. But some of you might notice it that I've not really, well, I've done all the definitions here, but I've not really defined what it means for left to win or right to win or whatever this is. And you would be right that I'm not, but I'm just going to leave that part for today. I'm not going to mention anything about that. That you should try to, in fact, you can try to come up with it yourself. You can try to come up with recursive definitions of what it means for left to win and right to win and so on. All of these things, instead of defining like this, you could give a recursive definition in terms of the left and right options. But for now, I'll just leave it as this with a very intuitive understanding of what all of these mean. And once I have all of these, I can now give the order for anything. So now I can compare any two games. G is bigger than h if g minus h is bigger than 0. G is smaller than h if g minus h is negative. G is equal to h if g minus h is 0. And G is confused with h if g minus h is positive. Okay. And then there we also have our definition of equality. Sneaked in. So I've defined two games to be equal if they are different is a second pair game. And this definition seems very strange. I mean, sure, it's what we have been working with intuitively and heuristically, but it doesn't really make sense why one would want to define that this way. And that's why I want to mention this alternative equivalent definition, which one can prove. I'm not going to do it, but and all games, even if I didn't mention this, all games that we will work with are short. So for all short games, X. So G minus H is the second pair if and only for all short games X, G plus H, X and H plus X have the same outcome. What is outcome? Outcome is one of these. If you ignore all of this, certainly in fact, you could prove this yourself, it's a silly exercise. That for any game, for any short game, one of these will happen. Either left can win no matter who starts, or right can win no matter who starts, or the player to move segments, or the player to move first wins. So in that way, so outcome is just one of these four possibilities, and then this is a second pair win if for all short games X, G plus X and H plus X have the same outcome. So they all, yeah, and this makes the definition more clear, because all that is really saying is that I'll call G equal to H if in any disjunctive sum where I have G, I could just replace it with H and treat it the same. And yeah, and again, this just even reinforces the idea that the thing we care about is sums. Sums are very central to the theory. So we are calling two games equal if in a sum we can replace one by the other without affecting anything. So this is equality, and well, exactly. So what some people work with in the subject is you could just tweak this definition on your own, to whatever you want. So you say G is equal to H. If for all, instead of short, you could put some other class of games, and instead of sum, you could put some other kind of sum, and instead of outcome, so well, for example, this outcome is normal play. You could put measure play, or you could put some other outcome. So you could tweak this definition in several ways, leading to several different notions of equality. But yeah, so this is the one that we'll work with. And for just to avoid any kind of confusion, all that has happened so far is I have defined the set of all games. I have, with this, with this I have given it, okay, so let me put it this way. So I have defined the set of all games. I have given a binary operation addition on the set of all games. I have defined the game 0. I have showed this. I've showed, well, not showed, but it's clear, commutativity and associativity. And then now I have defined an equivalence relation on this set, given by this. I'm not showing that, but it's very easy to see that it is an equivalence relation. And once I have this equivalence relation, then my claim is now consider the set of all equivalence classes. Then this operation gives an operation on the set of all equivalence classes, in that if G is equal to G dash and H is equal to H dash, then G plus H is G dash plus H dash. One could check this themselves by looking at the fact that the difference doesn't change. And with all of this, all I've, again, so it's short, take the set of all short games, define equivalence classes, and now I have a group here, because I have an addition, I have an additive identity, and now you could see that if you have the game G plus minus G, it is a second pair ring, because let's say left goes to some GL in G in here, leaving this, and then right could just go to minus GL, which is here by definition. So, and GL plus minus GL by induction is 0. So, if left starts, left loses. Similarly, if right starts, right loses. So that is G plus minus G equals 0. And so we have given it a complete group structure. And from now on, we'll just, instead of working with this equivalence class, we'll just use equality for that equivalence, and and that's the point. And if you don't understand any of this language about equivalence classes and stuff, it's perfectly fine. All that has really happened is we have defined equality ourselves, and now more games are equal than they were on their fine. So, and then I'd like to address just one more thing before moving on. So, it might seem a little weird that second pair wins are all called 0, while first pair wins can be different. There can be multiple first pair wins, which we'll call distinct. And one might ask, why this? Because at least there is somewhat of a symmetry that, well, what is the difference between second pair wins and first pair wins anyway? So why am I giving all of them the same name if it's second pair, not really when it's first pair? And the reason behind this is really the assumption of normal play. And because that assumption tells us that 0 is a second pair win. If the additive identity is a second pair win, then well, the second pair wins are certainly more special than the first pair wins. So that's exactly why second pair wins are fundamentally different, because we have assumed normal play. Okay. So the next thing is Sprague-Grundy Theorem. What do I do? Let's say. Let's go between the title of the talk, the Sprague-Grundy Theorem. So what it really tells us is what are all the impartial games. As I mentioned last time, informally it's saying that every impartial game has the value that an impile does. So let's just define an impartial game formally and then we'll start talking. So definition: G is impartial if the set of the left and the right options are identical and so I'll I'll call G impartial if the set of all left and right options are identical, GL and GR are identical, and everything in GL or GR, the same thing, are impartial as well. Everything there is impartial as well. And again, in the true spirit, another inductive definition, because to see if G is impartial, I need to check if GL and GR are impartial, and that I can do by induction because the GL and GR are born before G is, and so I could check that inductively. So this definition of impartial makes sense, and once I have this board is closed. Once I have that, now well, there's a very natural sort of question, which is can I somehow classify all the impartial games? And the Sprague-Grundy theorem exactly tells us how to do that. But I don't want to write the statement of the Sprague-Grundy theorem because at first glance it might seem very, very unmotivated. So that's why I want to motivate it first. So let's just try to figure out the impartial games born on the first few days. Day 0. We have the only game we have on day 0 is 0. 0 is impartial because the sets are identical, they're both empty, and everything there is impartial because there's nothing there. So this is impartial. Okay, and I keep forgetting. Let's just do a sort of a use of notation. If G is impartial, let's not repeat things. There's no point in doing that. So let's just write the set of options once. So 0 is this, is impartial. On day 1 we have 3 games. One, -1 and star. One is not impartial because the left and right option sets are not identical. Same for this. Not impartial, not impartial. Well, this is impartial. 0 is impartial, and the set option sets are identical. And so we'll just write this as 0. Okay. And then next thing, next day. Now we'll just so if I am to make an impartial game, I have to put some impartial games there and on the same set. So here I really have 4 possibilities, which is I only have 2 impartial games so far, and so I could now come up with 4 new impartial games. Well, not really new because this is 0, this is star. So at least I come up with 2 new impartial games on day 3. On day 2, sorry. But unfortunately, if you notice, this is a second player game. Why? Because and let me mention one more thing. So if G is impartial, impartial games cannot be positive or negative. That makes intuitive sense because left and right they have the exact same set of moves available at each step. Sure at T, and since every option is impartial, at any option, at any stage of playing the game, this condition ensures that left and right have the exact same set of options available. So that's why an impartial game is either 0 or fuzzy. One could write down a proof similar to the chomp argument that we had last time. Well, if G was positive, then there's a winning strategy for left on G. But then right could follow that winning strategy starting first. So if right starts first, right could win, but that cannot be possible. So certainly G is, so then in that case, well, G is fuzzy. If G is impartial, it's either 0 or fuzzy. And with that, and this again corresponds to second clearance. This corresponds to first clearance. A distinction between left and right is in some sense lost for impartial. Okay, so here, let's see. The first player to go has to go to star, that's the only choice available, and then the next player goes to 0. Star from star, you could go to 0, and so the second player wins. So this is the second player wins, and so it is 0. What about this? This I'll tell you that well, it is not 0 or star. It's a new game, and I'll give this a name. I'll call this star 2. Now, this is for you. I leave it to you to check that this is indeed not equal to 0 or star. Okay. And now that I've written star 2, you might remember the thing that I mentioned in the last talk, that to a nim position of a single pile of n coins, I give it the value star n, and you notice that right here, if I have a nim position, well, you notice a nim position with 0 coins is 0, a nim position with exactly 1 coin is star because there's only one move and that is to 0, a nim position with 2 coins in one pile is star 2 because you have 2 moves, to go to star or to go to 0. So this is exactly, star 2 is exactly the nim position with 2 coins, and then you see this pattern. So let's keep on going. There. Take 2, take 3. So far we have 3 impartial games, 0, star and star 2, and now we are going to construct more. So we have, well, the 4 that I've already written there are already there, but now I have written 2 star 2. This, in the true sense, in a similar script, we'll call this star 3. Star 3 is the nim position with one pile of 3 coins, because the moves are to star 2, star or 0. While what about these two? Well, certainly they are new games, right? They are not. Why? Because look at this. This is exactly the same reasoning as star. This is 0. The first player goes to star 2. I could draw that. The first player goes to star 2, the next player goes to 0 and wins. So this is 0. For this, what about this? Same thing. If you go to star or star 2, it doesn't matter. The next player can always go to 0. So this is 0 as well, right? And so two of the new games, two of the impartial these games, which we hoped were new, are not new, and they are just really 0 in disguise. What about this? This is certainly not 0. It's a first player win, because the first player to start could simply go to 0 and win. So it's not 0. But unfortunately, it's not 0 either. It's just star. Why is that? So let's write down a proof. So if we want to show this, we have to argue that this is a first player, it's a second player, it's 0. But minus star is just plus star. In fact, this is true for all impartial games. Why is that? Because argue by induction as usual. Suppose left starts, left goes to GL plus G. Right just goes to GL plus GL, because GL is the option for right. So if left goes to say H plus G, H is somewhere not it's not H. So from left option GL plus G. Since these two sets are identical, right foot follow up is going to GL plus GL. GL is impartial by definition, and by induction GL plus GL is 0. So it's a second theorem. Coming back here, for star it's even trivial, it's more trivial to verify because star is just 0 bar 0. If you take the negative, you just have to swap these, put a minus, minus 0 bar minus 0, minus 0 is just 0, so it's just star. So you have 0 comma star 2 plus star. And okay, so let's see what are the available moves. One moves to go to 0 plus star, one moves to go to star 2 plus star, and one moves to go to 0 comma star 2 plus 0. Correct. Okay. What happens in each of these? I want to show in each of these the second pair when you follow. In this, it's very simple. It's star, so I just follow up with 0 and I win. Here again, just go to 0 here and go to 0 and win. Here, go to move in star 2 to star and you end up with star plus star and then 0. So this is really 0 and therefore this is true. Fine. Okay. And so now when you notice that the only new impartial game born on day 3 is star 3. And by now one should be easily making the conjecture that on day n the only new impartial game I get is star n. And so let's recursively just define star n. Star n is 0, star. Star n is the impartial game given by where the moves are 0, star, star 2, dot dot dot, star n minus 1. It's impartial because induction, and this clearly is the in position with n coins very clearly. Perfect. So now this conjecture, let's try the conjecture as well. Conjecture. G be a short impartial game and G is star n for some integral G. This is a very natural conjecture, and here's the thing. This is exactly Sprague-Grundy. So the Sprague-Grundy theorem asserts that any short impartial game is equal to one of these star n's. Star n's are called nimbers for a very obvious reason. They're called nimbers. So this is the theorem, and before going to the proof, I'll do some more motivation. Before doing the proof, let's just if I could present the proof as it is, but I want to show how one could have come up with it on their own, so that argument doesn't seem like that. again we'll proceed by induction. We want to proceed by induction. So suppose this is true of all games born before some day n, and let's say you have a game born on day n plus 1 or something. And it looks like star n1 comma dot 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 star nk, where all these are born before, and just let me just mention this for the sake of star 0 is 0 and star 1 is 1 star. Yeah, very clear. So I don't need to worry about writing 0 and star separately. So let's say you have this. I want to say that this is equal to star n for some n, but I don't know what the n is. So let's work backwards. Let's suppose that this is equal to some star n. What could n be? So if this is equal to star n, then the difference is 0. But again, minus of star n is star n. Again, if you want to, if you don't understand that, you could just look at this again. If you just take the minus here, you will have to take the minus of all of these, and by induction the minus of all of these is themselves. So by induction minus of star n is star n. Perfect. So I have this right here. Okay. Now, okay. So I want to say that it's a second term. What are all the possible moves? A move is of two kinds. Is to go to star mi plus star n for some I, or to go to either to move here to this, or to here, or in here to go to this, where k is something smaller than n. I want to say that the second pair has a winning counter in either of them. Okay, so first look at this. Star mi plus star n is really just this position. Mi coins here and n coins here. This position, by our analysis in the last class, we know that it's 0 if and only if mi is equal to n, it's non-zero otherwise. So, and again the winning strategy was to just make them equal. If they are not equal, then it's the first pair win, the first pair just makes it equal. If it's equal, then the second pair wins. And here, there's exactly the same thing. So, well, if mi is equal to n, then the first player just wins here, because, well, yeah, if there are any mi which is equal to n, then the first player wins by going to this, which is because this becomes 0. So the first thing that we want from our n is, okay, let me write it down here. The first thing that we want is that it's not equal to any of the mi's. And once it's not equal to any of the mi's, well, the second player can now win. One of these has to be bigger than the other. You just go to the smaller one. So if mi is bigger than n, you can go from star mi to star n. So you leave star n plus star n, which is 0. If this is bigger than this, you go to star mi plus star mi, you make it 0. Either way, you can make it 0. What happens here? So here the winning move, well, I can't see it immediately, but there are two kinds of moves that can be winning. One is to go to star mi plus star k, and the other is to continue moving in that. Okay, let me not use the same k. Let's write something. Let's write j. Star L. The moves are of two kinds, either to star mi plus star k, or to star mi dot star nk plus star L, where L is something smaller than k. This cannot be a winning move. Why? Because if this was a winning move, then this would be 0. But if this is 0, then the first player could have gone to this in the very first move. You know, sort of like a chop argument. So this cannot be a winning move at any cost. This has to be the winning move. But what does it mean for this to be a winning move? Again, the same argument as here. This means that this is equal to 0, which means mi equals k. So same thing that we want is that for all j is smaller than m, okay, not k. Why did I write k? For all j is smaller than n, so what do we want from Rn? We want that it's not equal to any of the mi's, and everything smaller than it is equal to some mi. In other words, that the smallest non-negative integer that is not one of the mi's. So I could write down that. Okay, so let's just go to the proof. Again, to repeat, just to be complete, I said that pick an impartial game. By induction, all of its options are, since all of its options are impartial, by induction they all are numbers. So they all look like this. I want to say now that this game itself is a number. So now let n be. Now I want n to be such that these conditions hold. There could only be one such n, because if there are two, then you just pick and for the bigger one, the smaller one wouldn't satisfy. Anyway, so let n be the smallest positive integer that is not mi's, one of the mi's. That's exactly what we want. And in other words, this is the standard terminology. It's called the max of m1 to mk, mex, and this just means m means minimal, x means excluded. So you pick the minimal excluded non-negative integer from the mi's, that is your n. That's right. And then I want to show that that is true. In other words, I want to show that this game is 0. And why is that? The first player has two choices: to go to either star mi plus star n, in which case, since n is not equal to mi, this is non-zero, so it's a first player win, so it's done. The other move is like this, of this kind, but since it's the max, there is some mi which is equal to j, so you just go to this that mi. You just go to that particular mi, so it becomes star j mi plus star j, which is 0. And then this completes it. And you can notice that that these things here, we can now use the max rule very well. This is sometimes called the max rule. So now we can use the max rule to do all of this. What is that? It's the max of 2. Well, what is the smallest non-negative integer that is not 2? 0. So it is 0. Here, what's the smallest non-negative integer that's not 0 or 2? That is 1. So it's star. Here 0. And here, well, what's the smallest non-negative integer that is not 0, 1 or 2? It's 3. And so this is star 3. And so on. So this is the proof of Sprague-Grundy theorem, and let me just write down a couple more examples. So, what is the max of 2, 3 and 5? That is 0. And what this tells us is what about something like the smallest integer that's not here? 2. So is a Sprague-Grundy theorem, and so all short impartial games are numbers, and this makes their study very easy because, well, understanding numbers is already it's an easier task, and in fact we have already done it from the discussion in last talk. We know this. Starting is exactly this. Why is that? Because if I just look at the difference, and that is a nim position where there are n points here, and n some m here. The nim value of this position is n nim some m, which is 0. And so this is a 0 position. So in today's language, it's a 0. The difference is 0. So this is. So we now understand how numbers add. Comparison is very trivial, and so studying impartial games sort of becomes quite easy now. Okay, and then so this is mostly it for today's talk. I want to make a few concluding remarks for today. And the first thing is, well, this certainly helps us in studying impartial games, but still there's a lot of work that needs to be done, because even though in theory I know that my game is equivalent to star n, finding that n is very difficult. Finding that n is a difficult task, computationally as well. Because for that I have to do is I have to know the so let's call this the Grundy value. It's called the Grundy value for a short impartial game G. The star n is called the Grundy value of G. So to find the Grundy value of G, I have to find the Grundy value of all of its options. And then to do that, I have to do the Grundy values of all of their options, and that's a very so once I do this, it's very fine. But doing that is very hard because the number of options grows a lot. So there's that, and another thing is that, well, certainly this theorem helps us in studying impartial games, but it also helps us in studying non-impartial games that are not impartial. Somehow, there's a theory of atomic weights where you study these things called infinitesimals, and and the way to study those is use atomic weights, and the theory of atomic weights crucially uses these numbers, and numbers are very central to that theory. Okay, and one more thing is that the construction of games that we mentioned in the very beginning, where I take two things that way, it is quite similar to the construction of von Neumann ordinals, because if I just ignore, so the integers are constructed recursively, right? So because I have 0 equals 1 equals and so on, n equals this, but in fact turns out that I could, without violating equality, write n is this, and so on. And this construction, if I just ignore the second bracket, the nothing after the bar, this is exactly the construction of von Neumann orders, but you have to formalize it. That takes a little more work, but this is essentially what von Neumann ordinals are. And another thing is that if I take care of both brackets, but I impose another restriction that every game on the left is strictly smaller than every game on the right, then what I end up with is our familiar numbers. That is exactly the definition, somewhat the definition of a number, and those are called surreal numbers. Well, if we just drop the assumption of short, then those are called surreal numbers. And as you saw, that expression for 1/3, that somewhat resembles this thing called Dedekind cuts, and so this construction somewhat resembles Dedekind cuts in some way, and so this construction is very, very general. In fact, it leads to this field of all things, the field of all surreal numbers and stuff like that. And okay, and the final thing for tomorrow's talk what we are going to look at is simplifying games. As I mentioned at some point that we had this very 3x2 grid, dominating grid, it had a very complicated value. There are ways to simplify games, and the central question is that given a game G, I have several games that are equal to it. What is a very natural representative of these equal games? And that is what we are going to answer tomorrow. It's called the canonical forms. Canonical forms are very common in math. I mean, you see them in, say, linear algebra, where you have things like joint canonical form, or you have several kinds of decompositions which allow you to study those things in a very natural way. Jordan form, for example, is just expression of a linear transformation on a very natural basis, and stuff like this. Canonical forms are very recurrent in math, and canonical forms of games is what we are going to see in the next one. So for today, that's it.
So anybody has any questions? No, then let's time to speak.